All right, I think we're going to go ahead and get started. Welcome to another session of Nano at Tech seminars. Before I introduce today's speaker, just a word about the next one. We will be meeting in 2 weeks on November 28th here after Thanksgiving, and the speaker will be Professor Jason Azulai from chemistry and biochemistry. So it's a pleasure to have Mike Filler with us today, my boss. And Mike got his bachelor's degree at Cornell University and then his master's and PhD at Stanford, all in chemical engineering, before doing a postdoc at Caltech and then coming here to Georgia Tech, where he is currently, as you can see on the screen, professor and Traylor faculty fellow in chemical and biomolecular engineering, as well as interim director of IEN. Mike has won a number of awards, both for research and teaching, including an NSF Career Award. And with that, I will turn it over to you.
Great. Thank you, David. Thank you for the invitation. Thank you all for coming. I'm excited to share some vignettes for a broad set of projects that I've been working on with some collaborators the last couple years. And I chose an intentionally provocative title, $0 Transistors. I'll tell you more about what I mean by that in a second. But let me start by thanking the students who are current and former who have contributed to the data I'm going to show you here today. And I'll show pictures of them as we get to their respective parts, and then to some of the collaborators that I have the pleasure of working with. None of this would be possible without this collaborative team of folks, and it's really a joy to work with them day in and day out. So to get started, I'd like to talk about this gentleman. Does anyone know who this is? One of my personal heroes. That's George Eastman. George Eastman, the inventor of the Kodak camera. And you know the Kodak camera. That's because we tend to index on the thing, the camera itself. But what Eastman did was he invented an entire new process for photography. Okay? So before Eastman's time, photography was expensive, laborious, and very few people had it done. It was a very integrated process. You had to be an expert, bring in all the chemicals and all the materials to make the photographic plates. You had to know how to take the photograph, and you had to know how to develop the photograph. And so what Eastman realized was that you didn't have to do it this way. And if you were smart about it, you could divide up this integrated process into 3 separate steps. Okay? So I think you know what those steps are if you were born anytime before the year 2000. That was film manufacturing. It was the actual taking of the photo, and it was the photo development or manufacturing process. These were the 3 steps. And to do this, he not only had to invent the middle step, which was taking the photo with the Kodak camera, but he had to develop new intermediates so that you could pass material from one step to another in space and time. This was the innovation. And it transformed the world. So we scaled the ability to take and manufacture photographs by so many orders of magnitude that it led to a qualitative change in how humans view themselves in the world. It was dramatic. And this kind of factoring, while on one hand seems very straightforward and very simple, has a lot of, depending on what you're trying to factor, has a lot of interesting science and engineering that you need to consider. But there's been plenty of examples throughout history where similar factoring has led to transformational change. Okay. So the team that I've been working with has a goal, and that goal is to allow microelectronics to be made anywhere, anytime, by anyone. It's a lofty goal. It's a long-term goal. But if we think about making microelectronics through this lens, I think it informs a lot of how you might go about doing this. So today's market is a remarkable feat of human ingenuity. Right? We have all of these devices in our pockets, in our cars, all over the place. And I'm going to put all of that in the upper left-hand quadrant of this plot. Right? So this is a plot of devices in each circuit. Right? Today we have billions. And on the bottom is customizability, manufacturing speed, other metrics that we don't tend to 1 second. This is pretty annoying for everybody, probably. Okay. Let's go way down. How about that? Okay. So there's a big white space down in the bottom right-hand quadrant, I would argue, where we have the ability to make more customized circuits, where we can manufacture them much more quickly than we can today, among other metrics. The kinds of things we're thinking about, right, are maker spaces where you can make microelectronics, right, where each unique circuit is a couple bucks, right, at a micro scale circuit, just to be very clear, not PCBs, microelectronics, it will be a couple bucks. Where you could make them in a matter of minutes, so you could imagine a future where, I'm sorry, this is frustrating. Which microphone is it, Dave? I don't know. Here, I can do it like this. Let's try this. Okay, I'm just going to put it further from my mouth. There we go. I think that's better. Okay, where you can go to the doctor's office and they could make a customized electronic circuit for an e-pill or something similar to your anatomy, your disease state, et cetera. Instead of talking about learning to code, where we talk about everybody learning how to fab microelectronics and probably the intersection of those two things. And ultimately, if we're going to go to space, there's few things I'm sure about in this world, but I'm pretty sure we're not going to take a $20 billion fab that's about 1 kilometer in size to space. So what do you do? Well, I'm going to argue it's not a materials problem. It's not silicon's fault. I'm going to argue it's a process issue, and one that despite the transformation that we've seen from the existing process, there are other processes you could envision that may provide access to this space. Okay, so you have to understand what our current process is, what are the foundational tenets of it to understand how you might change it. And we, here today, sit on top of 70 years of innovation around the planar process. So the planar process was 2 key innovations, and there were several other things going on at the same time, but 2 foundational innovations in my mind. One was Ernie's planar process. And Ernie was the first person to realize that if you embedded devices into a semiconductor wafer and protected them from the outside world, they performed really well relative to the mesas of the time, which were fabricated on top of wafers. A nice side benefit of the planar process was that the top surface remained planar. It was flat. And so if you're Bob Noyce, you recognize in that moment that all of these devices embedded in wafers could be interconnected with each other lithographically, because the top surface, with the manufacturing technologies of the day, was now something you could work with. He had to do other things in terms of isolation of neighboring devices and other things like that, but he realized you could wire up these devices. That's the planar process. It obviously changed the world. I would argue that almost everything we've done since that time still relies on this basic concept. The planar process, for all of its success, has limitations. It looks a little bit like what photography looked like in Eastman's time before the Kodak camera. Everything's very integrated. We put in a whole bunch of feedstocks from a whole bunch of places, and out the other side comes monolithic integrated circuits. Wrong way. Okay, so number one limitation of the planar process is per step perfection. Requiring 1,000+ steps to be pretty much perfect is kind of crazy, right? And that limits how fast you can make things. It limits how cheap you can make things, and it certainly limits how flexible you can be with mixing and matching of materials. The other part is that there's no natural breakpoints in this process. So Intel has to know how to do absolutely everything. And we think of it kind of as normal today because they've largely figured out how to do that in a lot of ways, right? But that is weird in pretty much most other manufacturing paradigms. And I think sometimes Intel and others would prefer to allow someone else to specialize in an area that they don't want to be an expert in. So when you have this structure where everything has to be done by one entity, it's a huge barrier to entry. It's hard as a new company to make a dent and a contribution if you have to be an expert in everything. It also requires complete interstep compatibility. You're doing all these things together, and steps here need to work with steps there, And that will always be the case to some extent, but it's very tightly coupled today. Back in Noyce's time, people would talk about the tyranny of numbers. How do you interconnect lots of devices? And I would argue we today have a tyranny of integration. Things have to be too perfect, the process is too tightly coupled, and that limits some things that we would like to do with microelectronics. Okay, so what we've been trying to do is develop a factored process for microelectronics, right, where we factor component fabrication and circuit manufacturing into separate sets of steps. And we would do them in space and time with separate spaces and separate times. So the first part is the hard part, working with semiconductors, HF, high temperatures to have low interface state densities when you're building devices and things like that. We're going to leave that to the experts, like film manufacturing, right? And then there's the circuit wiring part. I would argue, and anyone who's been paying half attention to advances in additive manufacturing would say that I think this is going to become possible pretty soon on the desktop, just printing down wires. And so the basic idea is that we can fabricate components first. They'd be modular components. They'd have all the things you need to wire them up when they're sent to the printer. You wouldn't have to make any more metal semiconductor contacts or anything like that. That part would be done. And you would rely on high resolution wire printing to wire them up. Some things that this kind of paradigm would enable, in our mind, distributed and on-demand circuit fabrication. Okay? We can distribute dispersions or inks of components to people who load them into 3D printer-like machines and on-demand print them wherever they are. Natural heterogeneous integration, because you can imagine a series of inks, right? Different kinds of MOSFETs, memory, whatever, and you could print them and wire them up together, whereas today that is a bit hard, particularly when you're talking about different materials. So those are two key things that we think this will enable, and I'll come back to some other things in a minute. So that's the basic idea, and probably the first thing you should do, and those of you who know that we've been working on this for a while know this wasn't the first thing we did. I'm glad we've started to work on this because it helps say we're not nuts, is to show that the whole thing could work. So here what I'm showing is work from a student, Hubert Ellie, where he's used traditional top-down fabrication technologies with a wafer to fabricate micromodular transistors. And what you're seeing there is a section of an array. These devices are fully operational. They have all the components you need, right? The full gate stack, the full metal semiconductor contacts, they're all ready to go. He's developed also a process where he can transfer them to different substrates. Okay? So he can take them off on, say, a PDMS stamp, and he can put them on glass or paper or other things like that. So there are the modular transistors on silica. That's kind of the first part of this process, right? And if nanomodularity one day is going to work, these better last long enough that we can print wires to them and they can maintain their performance. And so now what happens is you partner with FedEx and you ship these to your partner, okay? And so we ship these to our partner at the University of Michigan, Keir Barton, who is an expert in a technique called electrohydrodynamic printing, which is basically high-resolution additive manufacturing. And you can see this picture of their tool. It's a research tool, obviously, but it fits on this desk right here. Okay? And as opposed to something like inkjet, which uses a pressure differential to push ink out of a nozzle, eJet uses an electric field to pull ink out of a nozzle. And it allows you to get to really fine line widths. Okay? So this is showing down to nearly quarter-micron metal printing on the desktop. Also point out that it just prints what you want. This is one of those additive techniques that doesn't have a lot of waste. It just prints metal lines, which I think is important if you're talking about distributed manufacturing. Okay, so they are not experts in electronics. They take our modular devices that they received on these different substrates. They put them into the printer. They print lines, and then we partner with FedEx again, our close collaborator, and it comes back to Atlanta, where these are measured in Eric Vogel's laboratory, right? And so what we're showing here is standard IV characteristics for these devices. They were made, they were transferred, they were shipped to Michigan, they were shipped back, and they still perform pretty well. This isn't going to break any records. This is not going to be in an AI chip, but this is pretty good performance, really reasonable mobilities and subthreshold slopes if you're trying to develop an on-demand technology. And we've made some simple circuits. So this shows, in my mind, we're not nuts. We can factor the process steps into two groupings, the component fabrication and then the wiring, if we think smartly about where to divide them up. Okay. That's great. But that's not going to, in my mind, sticking with wafers while maybe in the short term can yield some dividends. If we really want to make microelectronics made anywhere, anytime by anyone, we're going to have to think differently, not just about the wiring and the splitting of these things in space and time, but we're going to need new processes to build the components. Okay, so the easiest way to understand this, and this is how a chemical engineer views the world, is in how much it costs for feedstock per kilogram of feedstock. Right? So in this new process, we're talking about transistors as a feedstock. Okay? And just so you have a sense for where today's transistors stand in terms of their cost, let's compare them to some other feedstocks. So the active ingredient that goes into Lipitor, which is an anti-cholesterol drug, is about $2,000 per kilogram, which is really expensive. It's a pharmaceutical. Right? Methanol or something simple is like $20 per kilogram. Just so you have your bearings, gold is about $50,000 per kilogram. Okay. I'm going to argue that if a core feedstock for your process is as expensive as gold, it's going to be a challenging process. And so modern MOSFETs are about $10 billion per kilogram. All right, this is taking a TSMC process and looking at the cost per wafer and how many devices are on there and how much silicon that takes, and very quickly you can do a back-of-the-envelope calculation and you see it's billions of dollars per kilogram, which is not going to be so amenable to microelectronics everywhere by anyone. So the final thing we need to do or recognize in the planar process is that it's a planar process. So it's right in the name. It's so obvious it's hidden that we do everything in 2 dimensions in semiconductor manufacturing. And so if you do something in 2D, and by the way, if you to get a sense for this, think about the holidays coming up, right? When you're cooking something for a bunch of people coming to your house, are you cooking it on a flat frying pan kind of thing, or are you cooking it in a big vat? You're cooking it in a vat, right? So 2-dimensionality limits scaling. So the last thing we're going to need when we break apart this process into 2 sets of steps are bottom-up or bulk component synthesis. How do you make transistors in bulk? And ultimately, I'm not going to have time to talk about opportunities for error correction, really separation. How do you deal with imperfections in that process? Assuming you're going to go into this process and there will be imperfections in how you build in the components. There'll be a distribution of properties. By the way, that's how all manufacturing works except microelectronics. But I'm going to leave that last bullet for another time. But let's talk about bottom-up and bulk component synthesis. And this is where the idea of $0 transistors come. Because my argument is if you can scale up production by orders of magnitude in the bulk using bottom-up chemicals-like processes, you can drive down the cost of transistors by orders and orders of magnitude. And it would be effectively like they were $0. They'll never be $0, but as close as they could be relative to billions. Okay, so we're going to talk about how we do this. How do we make a bucket of these components? And for those who don't know much about transistors, just to kind of make sure we're all on the same page, you need 2 major things when you're building a MOSFET. You need a semiconductor, which has a high mobility, which means the charge carriers move through it really quickly, so it can switch fast. And you want the distance, this middle region here, over which they're transporting to be as small as possible, so they can move across from one end to the other quickly. That would be the gate length. And so small gate lengths and high transport speeds, and we're going to continue to focus on silicon. You know, it's maligned in some circles, but it's a really remarkable semiconductor with a pretty decent mobility. Okay. So I'm going to show you a process we've been working on where we start with a seed or the goal is to start with a seed particle, to use a crystal growth process. where my group came to a lot of this was from our growth of crystals, where we can program the composition along the length. And then I'm going to talk about a patterning process we developed that allows us, without photolithography, okay, to mask the source and the drain of this transistor we're growing, so that we can protect them from the deposition of the gate stack. And ultimately, you would think about taking off the mask, and probably need contacts. They're not shown here in this picture. Okay, so let's talk about the crystal growth. Right, so this is a technique called the vapor-liquid-solid growth technique, where we start with a seed droplet and we deliver semiconductor precursors, here in the form of silane, from the vapor. So it's a CVD process. And we can co-flow with the semiconductor species dopants, so phosphine or diborane in the case of silicon, and we can, in space, and not in space, but in time, we can control what we're flowing, and we can create source channel drain along the length of this crystal as it grows. And these are just pictures of wires that are obviously more than single sets of source channel and drain. Bless you. They have been selectively etched afterwards to reveal the lightly doped P segment in the center. But that kind of gives you a sense for the precision. And I'll point out, right, we haven't tried really hard, but we're able to get dimensions between a source and a drain region of 100 nanometers. One of the first questions is, okay, now you're growing crystals with a seed particle. Is the material you're making going to yield high-quality transistors? And so Siddharth has done a bunch of work taking bottom-up grown wires and applying top-down fabrication techniques to build MOSFETs out of them, just to prove out that the materials, the nanowire materials are good for what we're trying to do. And so again, you see IV curves. And here he's characterized, the types of scattering processes that might be limiting us. But the bottom line is we're getting hundreds for mobilities and decent on-off ratios when we do this. So we're not really worried that the crystal growth is going to be limiting in any way, shape, or form. Okay, so now the patterning step. We can't use photolithography. It's inherently a two-dimensional technique. We need to do something to direct how we build key features without that technique. And so we've developed a technique we call scales. It's a chemical lithography. And so I'll explain to you what it is by analogy to conventional photolithography, which you know, I think probably if you're in this room, you know the top line really well. So we're going to do something similar where we take our nanowire that we've grown with source channel and drain, and we're going to grow off of that surface a polymer. It'll be everywhere, a lot like when you spin a resist on a wafer. The polymer will be everywhere on the nanowire. And then instead of using light, we use chemistry. So we apply a selective etchant. It's pretty similar to the one I had shown on a previous slide to make those undulating structures. But if you design the chemistry correctly, it will diffuse through this polymer, and it will find the underlying semiconductor. It will find the nanowire surface, and it will etch the lightly doped channel region, and it will not be able to etch the heavily doped source drain regions. And when it etches that channel region, because it's removing some silicon atoms from the surface, that's where the polymer is tethered to. Now the polymer breaks free from the surface and can be solvated in solution. And so here we started this process like a lot of our processes on wafers, because we have characterization techniques that allow us to look at this at the wafer scale that are really hard on the per nanowire scale. So this is on a wafer. This is a pattern wafer with some heavily doped regions and some lightly doped regions meant to represent the channel region and the source drain regions. And so here, after we do the polymerization, you can see the classic peaks of PMMA. And then we apply this selective etch technique. And sure enough, we're able to maintain the PMMA on the heavily doped regions, which is our goal, and pretty much remove it from the lightly doped regions. We see a little bit, by the way, the etchant is KOH based. We see a little bit of potassium here left over. But the basic concept works, at least on wafers. And again, just to remind you of what's going on here, on the heavily doped wafer, the etchant is diffusing through but can't attack the underlying silicon to which the polymer is attached. On this side, it can diffuse through and start to break the connection of the silicon to the rest of the wire, and in doing so, we start to remove chains into solution. So we can track this as a function of cycles. We do this process by which we do some KOH, and then we dip it basically in a developer of sorts to get some of the chains out into solution. And we can track this, and it goes as you might expect, right? So we have basically no change in the carbon 1s for the heavily doped region, and in the lightly doped region, we remove carbon. And we can track this with another technique like ellipsometry, and the story is pretty much the same. Okay, so now we have a mask on the surface, and the next step will be to see whether we can selectively deposit the gate stack. Again, trying to eliminate anything that's not a chemical process. So here on the bottom is what you're seeing in the hafnia and platinum regions of the XPS, so nothing because I haven't put anything down yet. And then the next step will be a hafnia process that we do here at Georgia Tech. And we can see that hafnia goes down on the lightly doped region, which was the one that we had just exposed, and it's pretty much blocked from the heavily doped region. And then we can apply the platinum process, and we can put platinum on top of the hafnia, and we don't get much platinum on the heavily doped region. So this is what those look like if you do EDS in the SEM. So we have these squares that are selectively deposited. And when we do capacitance measurements, we can characterize the capacitor and see, for example, that one, it behaves pretty decently. It behaves like a capacitor, so that's nice. Two, the interface state density starts, not great, but we can make it better with a forming gas anneal after the fact. Okay. So we're able to get interface state densities in the low 10 to the 11s, right? This is not breaking any records for sure. Right? But we can create these devices, and we can at least start to engineer their interface state density. I'm going to skip this. This was more work we did to try and understand how to engineer the interface. Okay, so that's on wafers. The real challenge is making this work on nanowires. And so there I'm showing a nanowire with a slight selective etching just to show where the P region is. Here is EDS in a TEM of a wire that has been selectively etched with the PMMA. And so what you can see is the red regions, the carbon from the PMMA, are still on the source and the drain, and a lot less is on the channel region. So we've been able to etch it off selectively. It's not perfect, but it's not horrible either. And when we do our selective hafnia process, we can grow these coaxial hafnia films around the region of the nanowire that's the lightly doped channel region. So this work is ongoing. We continue to work through a bunch of yield challenges and understanding how a nanowire is a lot different than a wafer. They're both silicon, but the morphologies and surfaces and structures are enough different that we have to work through those complexities. But we're on our way. Okay, so that is a bottom-up process to build transistors without photolithography. That's kind of step one. The other part was the do it in the bulk part. Okay, so we're going to cook in a vat on the stove. So how do we do that? This is important. So when people think about scale up, and you're talking about semiconductors, we're often thinking about roll-to-roll, two-dimensional manufacturing. It's still going to be 2D, but we're going to do it with such large sheets and over such fast timescales that we can scale it up. And this may work for certain applications. But I would argue in general you're fighting a losing battle for a lot of things because you have L-squared scaling, right? You only have areal scaling versus volumetric scaling. And if you can go into that third dimension, it changes things. So the question is for crystal growth and ultimately fabrication of these bottom-up devices, how do you go into 3D? And so we've developed a process we call the geode process after the geological rock formation. Right? So we all know what a geode is. It has this shell, and there's crystals that have grown inside this shell. And so we've been trying to do the same thing, but more on the micro scale. Okay? So on the left is a picture of what one of these microcapsules might look like, and I'll show you some real images in a second. They're about 30 to 50 microns in diameter. They have a porous shell that allows gas to transport efficiently from outside to inside. And we line the interior with the metal nanoparticles that drive and catalyze nanowire growth. Now, this is a powder, And what are we going to do with it? We're not going to put it in a traditional CVD system. We're going to put it in some kind of bulk chemical reactor system, more like you'd see at a chemical plant. And then we're going to grow crystals inside. We'll now have, instead of capsules, microgeodes when we are done with this process. And you could imagine homogeneous silicon wires or some other material. You can, in theory, hope to get the ability to modulate structure along the length and harvest them and even harvest devices out of there. To give you a sense of the scaling benefit that comes from doing this in 3 dimensions, if I have kind of a standard industry-sized reactor, actually it's pretty small scale of about 1 meter cubed, we can make as many devices in 1 day as the global semiconductor industry makes in a year. That's the benefit of 3-dimensional scaling. Okay, so how do we make the capsules? We have to start there. That is an emulsion templating process, which I collaborate very closely with my colleague Victor Breedveld and Sven Behrens. We start with a single emulsion, which are these water droplets in a continuous oil phase. And the metal particles are decorated with a molecule that makes them hydrophilic, so they're happy to go into those water droplets. The silica that's going to form the shell is slightly hydrophobic. It's happy to go into the oil phase. You do a second emulsification, where now you have a continuous water phase, and you can start to see what's happening in that second image. We're going to have the metal particles still in the middle. The silica particles will start to be compressed in the oil shell, and then you have this continuous water phase. If you're smart about choosing the oil and it's soluble in water, it'll start to go into the water phase and leave and coalesce the silica particles into the shell. And that's kind of what happens. And you have to dry it, and you end up with a powder that looks like that. And we can make a lot of this powder. We can make a truckload of this powder. This is a very small truck. It's about this big. But it's still a truckload. And that's what a crystal growth process might look like occurring on the inside of these capsules. I show the Raman on the right to show you their single crystal. And not because it's fancy, but because it's not fancy. Because the ability to take a pretty standard Raman microscope and measure that information, because I have a large quantity of wires, is really powerful. The large majority of people who work in the nanospace, particularly in the nanowire community, we struggle with characterization techniques to look at the single wire level because we just don't make much stuff. But if you have a scaled up technique like this, you can start to more quickly get insight into what's going on. Okay. It's obviously an average. You're not getting information about every wire in the ensemble, but there's a lot of value in quick measurement. Now, importantly, we want to make devices in here. Okay? And so this is showing the ability to program composition of wires grown in these capsules. So you might be thinking there's this wall. How in the world is that wall going to influence the growth process? And it turns out not much at all. The wall turns out not to matter, okay, to the growth. And I'll tell you more about that in a second. And so here, this is silicon and germanium modulated during growth, because it's a bit easier to see in the EDS. And sure enough, we can modulate composition along the length. We can do it uniformly. We can do it with varying lengths. This is all programmable very easily through growth. And here, inside geodes, we're able to get segments below 100 nanometers in length. So if you're thinking about a future channel of a MOSFET, we're able to start to get in theory, 100 nanometer devices. And this is what I said a minute ago. If you were to put a substrate next to the geodes without any geodes and look at wires grown on it versus wires grown in geodes, and then plot the length of the segments for the ones in geodes against the length of the segments for the wires not in geodes, there's really no difference. And why is that? It turns out transport through the shell is really fast relative to growth. Okay, so if you're that wire, you're getting plenty of material to go into that droplet and nucleate the next layer of the growing wire in the time scale it takes to nucleate. Okay, so it's not an issue. This is showing growth rate from a model we developed versus diffusivity. That's a reasonable diffusivity for walls kind of comprised of this size silica particle. The bottom line is, over a very wide range of diffusivities and wall thicknesses, the wall's not there. So if you had seen the image, you said, well, what if the wall, variations in the wall thickness, will that matter? Turns out no, because the transport is still really fast through the wall. Okay, and relatively recently, Caleb has been able to show that he can grow devices inside the capsules, harvest them, do electrical measurements on them, and they behave like nanoelectronic devices. So before we had the composition variation we could control, and now we are able to construct at least simple two-terminal devices inside these capsules. And so maybe not off to the races, but we're making nice progress towards our vision. We have this new reactor. In fact, it's just upstairs, one floor. If anyone wants to come and see it, let me know. I'd be happy to show you. It's a new rotary bed reactor, which is basically a cement mixer style reactor that we can load the powder into, and it spins while you're flowing these precursors across that powder. You need to have a certain amount of mixing in the bulk so that what happens at the capsule level is what you want. But we're really excited to be able to spend time with this system, which has just got installed. I'm going to skip that, and just a few take-home messages. So my contention is that microelectronics that you could make anywhere or any time would open up a variety of new opportunities. They will look different, and we will use them differently than the microelectronics we make today. Let me be very clear about that. The goal is not to replace what a company like Intel does, but in personalized medicine, in security, in all sorts of things where you want local fabrication and highly customized fabrication, I think there's tremendous opportunities. So we're developing this nanomodular approach. There's a lot of science and engineering that has to come together to make this a reality. There's no fundamental showstoppers in my mind. It's just a matter of a systems level engineering to make this work. And I also want to point out that I've talked a lot about silicon. And silicon's a really great material, but there's a lot of it. We can scale it. It's a good semiconductor. But everything I've told you is applicable to your favorite architecture, your favorite device operating principle, your favorite material. The idea of nanomodularity is agnostic to those things. Right? It's just talking about bringing more modularity into microelectronics manufacturing and the benefits that could come from it. So with that, I will thank the sponsors. Thank you for your attention, and be happy to answer any questions.
Questions for Mike? I guess I'll start off. Maybe I missed it. What's the material that the shells are made out of?
Oh, silica.
Silica.
Silica, yeah. There's interesting questions about alternative materials, titania or other things, or even shells that have a core shell structure. So you can imagine some kind of silica in the core and some other material around it that helps you break open shells. There's all sorts of fun questions we can ask, but right now they're just straight silica.
And I guess, so what is the harvesting process?
Right. So a couple things on that front. First thing is that there's applications outside of microelectronics where you don't need to harvest. So it turns out those crystals inside colloidal capsules are really interesting as processable optical materials. Right, so now that they're in these colloidal capsules and you can flow process them and engineer the optical response through the cutouts in the nanowires or the materials you choose or the core shell structures you might make on the inside, you don't need to harvest. On the microelectronic side, it's a really interesting question. How you do that well, how you stabilize the surfaces of the wires so they don't agglomerate. One of the things that capsules do really nicely, which I didn't say, it turns out to be more important than maybe it should be, is that it's almost like the capsule's a roll cage, and the nanowires, by virtue of them growing off the surface, are kind of seat belted to the surface. So if you were to just have them free floating in the bulk, they would collide with each other and stick during processing in a way that I think is going to be detrimental. So having them in there is great. They're seat belted, they're protected, gas diffusion is efficient, but getting them out, you have to figure out how to do. It also gets to my point about error correction that I was making. So for those who don't know, 15% of worldwide energy goes into separating things. It's remarkable how much energy we use to separate things. And that's because we tend to have manufacturing processes that just assume you're not going to make everything perfect. Whether it's tomatoes you're buying at the grocery store or parts for your car. And so I don't think when we harvest these things, they're all going to be perfect. I have no illusions about that. And so we're going to have to develop techniques that allow us to fractionate, right? Take the diodes, right? Can we fractionate diodes based on their built-in voltage? Assuming there's going to be variations in doping along the length or something like that. There are really interesting scientific questions, engineering questions you can ask at that front. So that's a long-winded answer to your question.
I think I can do without this. The assembly your collaborators do, is that a manual process or is it automated at this point?
Yeah, so soon we'll have some data to talk to this more specifically, but I can tell you verbally. So we've been collaborating with a group of folks in computer science who are looking at the question of, if I have this dispersion, right? Some of you are thinking, he told me he's going to make it in a vat, and I don't know how he's going to make a circuit out of it. And so imagine you take a dispersion of wires and you throw them down on a surface. Well, there's a spectrum of completely random to completely ordered as you would want them. And my sense is there'll be a range of technologies that one could develop. But let's take the completely random case for a second. If we're talking about a cryptographic key, all right, and I throw down some transistors that are completely random, I think the randomness is helpful. And it turns out, according to our colleagues in computer science, that they can route a 10,000 transistor circuit in under a minute with a single processor. So as long as you know where those devices went, right, you can route the circuit and print it way faster. Excuse me, you can route it way faster than you can print it. Right? But that's kind of, I think, what this looks like. At least in the short term, the most appealing short-term, near-term applications are kind of random placement of components and then wiring of those components into a certain circuit. But there's a lot of room for innovation there, I think.
So it's kind of like recursive problem for them. You just randomly throw them on a surface, then they find a way to route them that would work to the goal that you want.
Correct. Correct. There's interesting questions about how much time you want to spend routing and what wire length it ends up telling you need. Right? So if you have a really dumb algorithm, it may route them, but it may give you a wire length that takes 10x as long to print. Right? So there's these interesting trade-offs between the timescale of routing and the things like wire length that the routing gives you and the printing technique. So there's an interesting intersection there that we haven't really had to think about before.
All right, thank you.
Yeah.
Other questions?
And you're still thinking in 2D when you put them down?
Right, great question. So I would argue you could think of the component fabrication as 2D or 3D. I showed you 2D and 3D today, right? I showed you the micromodular devices were 2D fabricated in traditional sense, and I talked about the geode stuff. And then on the circuit side, I talked about all 2D on the circuit side. And yeah, I think there's opportunities in 3D. We're not really actively working on them, but that's more self-assembled circuits and things like that, which could come, but that's a different ballgame. But I do think modularity will help in the assembly of circuits in 3D.
Anything else? All right. If not, let's thank Mike one more time.